All right, y'all. So for the project associated with the energy unit, what I'm going to ask you all to do is to lift some weights. And I don't care what you actually lift. You could do push-ups. If you have access to some dumbbells, that's fine. You could lift a chair. You could do squats. I don't really care. Not sure why there's two S's on dumbbells. There should be two also. I don't really care what you actually lift, but you're going to pick up some object. It could be yourself or it could be something else, and you're going to lift it. And what we're going to do with this is calculate the amount of energy that you burn by doing this. So I want you to do as much as you can, all right? As much as you can. That means either picking a smaller weight and lifting it, 10, 20, 30, 40 times, or picking something as heavy as you can and lifting that. But to calculate how much total energy you're going to burn, we need to know the formula for gravitational potential energy. Because as you lift this object up like this, now it's got more potential energy. If you can calculate the actual number for that, that'll tell us how much energy you burned by doing so. So to do this, our very first physics formula, gravitational potential energy, you need to know three things. And the first thing that you need to know is what the mass of the object is. This should make sense to us that this would be involved because obviously the heavier the object is, the more energy it takes. Lifting a paperclip up doesn't take nearly as much energy as lifting like a big heavy weight. And this is science, and so we're going to use the metric system. Mass has got to be measured in kilograms. 1 kilogram is 2.2 pounds for our purposes, and so if you know the weight of the object in pounds, you're just going to do a simple unit conversion and turn it into kilograms. Second thing you're going to need to know is the height that you actually lift this thing. Now this will make sense because lifting something up just like an inch like this doesn't take much energy. If you lift it way up here, that's going to take more energy. And again, this is metric system because science, so we'll have to do it in meters. If you measure, if you don't have a metric meter stick laying around, you could always just measure it in inches and do the conversion. And 1 meter is 39.4 inches. The third thing that's going to affect how much energy it takes to burn is the planet you do it on. Because when you're lifting something up against gravity right here, the strength of the planet's gravity field will determine how much energy you have to burn. If you were to go to the moon or Mars or something, it would be easier. If you go to Jupiter, it's way harder. You all are going to be doing this on Earth, I think, and Earth's gravity field has a strength of 9.8 newtons per kilogram. We don't really need to worry about those units right there. The 9.8 is the important number. So I'm going to do a quick example here for you to show you how this works. I'm going to multiply the mass times Earth's gravity field times the height of an example lift that I'm going to do. So I'm going to reach over there and grab this 12 kilogram dumbbell. Sure. 12 kilograms times Earth's gravity, which has a strength of 9.8, times the height that I lifted. So I'm going to go and measure this thing, and it turns out this height from there to there is 0.4 meters. Sure, I'm just making up numbers right now. You'll actually measure the real thing. And when I do this, what I wind up getting is 47, right? 12 times 9.8 times 0.4 winds up being 47 somethings, 47 units of energy. Well, in the metric system, the unit for energy is known as a joule. It's named after some scientists from the 1800s. It's spelled Joule, but it's pronounced joule, like a precious gem. That's easy enough to remember. Energy is precious and valuable, and we're trying to save it, just like we would with actual joules. So I would say that this is going to be 47 joules per, oops, that's not what I meant to do, 47 joules per lift, because this is the formula I would use to figure out how much energy I burned doing it one time. If then I wanted to, say, lift this like 30 or 40 times, what I would do would be to multiply that fraction by the number of lifts, right? And I can see how lifts cancel and it leaves me with the total amount of energy. So let's say I do this thing, the 15 times. Sure. I would simply multiply 47 joules per lift times 15 lifts and get some huge number. I can't do that in my head, but I have a calculator handy around here somewhere. Or I thought I did. Yeah, there it is. Times 15 winds up being something like 700 total joules of energy that I burned by lifting this weight on this planet this far, this many times. So you're going to do that for your activity. You're going to actually measure the distance that you lifted it. You're going to tell me how far your arms or your legs actually push this thing up. You're going to multiply it by Earth's gravity, and you're going to calculate the amount of mass that you are actually lifting. If you're doing push-ups, it's probably your body weight. If you're lifting a dumbbell, that's pretty easy because you have a number written right on the side telling you how many pounds it is. If you're lifting something like a chair or a little brother or something, you'll have to actually weigh it and make that measurement. So the unit of joules is the standard metric unit for energy, but it's not the one that we're all most familiar with. The more common unit of energy that we know, especially when it comes to food, is going to be a calorie. And any prepared food has to, by law, include nutritional information where it tells you exactly how many calories are in there. So this Clif Bar right here that I just took a picture of, 250 food calories. To be able to convert these and to be able to go back and forth between joules and calories, we just use the conversion factor that 1 calorie is 4,184 joules. So a food calorie is actually quite a bit of energy, right? Me doing these reps with a 25-pound dumbbell, 12 kilograms right there, lifting that thing 15 times, I only burned about 700 joules, which is going to be roughly 1/6 of a calorie. Like, that's not a ton of energy that I just burned right there. That's not really that heavy of a weight, and I didn't do it all that much. What I'm going to ask you guys to do is to look at the amount of energy you burned by doing your weightlifting, and I'm going to ask you to compare that to the amount of calories that you actually take in by eating food for one day. So this can either be a real day, you can either actually keep a detailed food log of what you ate in the last 24 hours, or you could just kind of make up a typical one. You're going to keep a log of all this stuff, or you can just make up a reasonable one. There's dozens of calorie counting websites out there. I linked you guys to this one right here on the actual assignment itself. This would be a pretty typical day for me though. Breakfast, 2 eggs, 2 pieces of toast and a banana. Lunch, I just have a chicken sandwich, and then salmon, salad, potatoes and ice cream for dinner. It'll come through and tell me that in that day, I wound up eating about 2,100 calories worth of food. So what I want you all to do is to compare the amount of energy that you ate, right? The amount of food calories, the amount of chemical energy that you brought in, and how that energy is converted. I want you to tell me that how much of that actually went to your lift, and then what else did your food energy go to? Now, you can do this using some sort of pie chart if you want to calculate those other values. You can do this in words. You could do it in a diagram, transformation diagram that looks like this. But what else did your breakfast turn into? I want you to be descriptive of the amount of energy that you burned by lifting the weights and the amount of energy that you brought in. So you're going to actually compare this number to that number and tell me why it makes sense about how big or how small it is, and give me some estimates for the rest of these right there. All right, that should explain this thing pretty well. Again, I linked you all to this website on the actual assignment itself in Schoology, and I'll close with just leaving the formulas up here for y'all to see.